Hello, my name is Carson McGuire, and for my MAE 535 demonstration, I've designed and built a simple alternator. Now, alternators are a type of electromotive force device that generate power by moving magnets past coils of wire. The principal behavior that allows them to generate power is described by Faraday's law of induction, which states that a time-varying flux linkage will induce a voltage in an electronic circuit. This flux linkage can be changed by varying the number of turns in the coil. So to increase the induced voltage in this alternator, the number of turns of wire could be increased. Alternators are typically used in cars to charge the battery in the car, or they could also be used as generators in energy harvesting systems. One such energy harvesting system is a coaxial turbine, which is a type of marine hydrokinetic energy harvesting system. Coaxial turbines feature counter-rotating blades, which increases the total RPM of the generator compared to single-rotor turbines, thereby improving their energy harvesting capacity. For the demonstrator device, I've designed an alternator that features two spinning discs of magnets and one disc of stationary coils. I've designed it so that the magnets pass over each coil. I've designed it so that two magnets pass over each coil at any given time, which increases the induction effect in the coils. And the magnets are mounted with alternating polarity so that the magnetic field actually changes as the magnets pass the coils. Here's a picture of the fabricated alternator. Every non-metallic part on this is 3D printed, and that includes the shaft. So first demonstration is with a 500 ohm resistor in load. A 500 ohm resistive load in series with the alternator. I've wired all the coils of the alternator also in series, so just to maximize the total induced voltage. There are, if you remember on this CAD model, there are 6 of these little clover leaves where the wire is wound into the coils. Each of them have about 200 turns of wire. So in total, in series, I get about 1200 turns of wire with 12 magnets on each disc. So that comes out to 24 magnets and 1200 turns of wire total. So what I've done here is put a 500 ohm resistor in series with the coils just to keep the current pretty low. And you'll see as I spin it, on the oscilloscope, I'm probing the AC output directly from the coils of wire of the alternator. You can see the oscillations in that voltage. As well, I have a full bridge rectifier circuit to rectify the AC to DC, and you can see that on the multimeter to the left. You see as I spin the alternator faster, the voltage on the multimeter increases, and I'll show that a little more clearly in a few slides. Let's see. Next is a demonstration with a 5 ohm resistor. So what happens here is, as I've dropped this total resistance through the system, I actually increase the current through the wire. The torque that the alternator produces is proportional with current. So I expect to see a higher torque when I spin this with a lower resistive load in series, and you actually do see that the oscillations, they damp out much quicker with this lower resistive load in series than they did with the higher resistive load. And finally, I've hooked up the DC output from the full bridge rectifier to a capacitor, which is then has a LED to dissipate the power. You'll see as I spin this, the power across the capacitor ramps up, which is shown on the multimeter to the left, and then slowly dissipates over the resistor, over the LED. You can also see the little red LED lighting up whenever I spin the alternator. And that's shown a little bit more clearly in this video. All right, thanks for watching. Bye.